So as it says here, when the periodic table was made, it wasn't put in the arrangement that it's in because we knew electron configurations or had PES data. And in fact, it was before even knowing that protons and electrons existed. It was all about chemical reactivity and the ability to form compounds. In fact, the noble gases found their place on the periodic table later than many other elements because they were so unlikely to react and form compounds. So when we are thinking about these trends, it's mostly about the ability to react and ability to form chemical bonds and compounds. That is the most important application. When we get into bonding and distinguishing between ionic, metallic, and covalent, it's important to think about these trends, Zeph and shielding again. So when we are doing that, the most important way that we can group elements is to think about vertical columns, vertical groups, vertical families. The similarities in electron configuration, valence electrons, means that they form similar compounds. So whether we're talking about metals and what ions they normally form, or a non-metal and its ability to either form an ion or to share electrons and form a covalent compound, there is a pattern that we see there, and that's probably the best predictive power that we have. So when you are asked which two things are most similar, the most similar are going to be the things as close as possible to one another in a vertical column. A slight exception to that is with the transition metals within a same row, because of the way the shielding and Zeph works, they are similar, but that's much less kind of important and predictive than what we know from columns. So we have used these terms a lot. They are familiar from previous classes, hopefully, and previous years, but atoms will gain, lose, or share electrons, not because they want to, but because of energy changes and because of the forces of attractions predicted by Coulomb's law that allow them to do those things. When they become full, either by gaining, losing, or sharing, they are more stable. They're more what we would say is thermodynamically favorable. The things that don't react, like the noble gases, they don't react not because they're full, not because they don't want to, but because so much energy is required to make that happen that it is very, very unlikely. It goes from a stable place to a less stable place by putting in so much energy. We shy away from, in explanations, the want to gain, want to lose, want to stay the same, and favor the favorable to do this, or more likely to do this, or becomes more stable when this happens. So when we're looking at this, we do know that there are patterns. So metals tend to have very few valence electrons. And we've used this phrase, but just to restate it, that's the electrons in that outermost level, and we can count it across the periodic table as 1 through 8. The attraction is very weak. The ionization energy is very low relative to other things. So they are very likely in a reaction to lose them. So those small number of valence electrons means that they're going to become ions easily. They lose all of their valence electrons, and we can know their charges. Alkali metals, 1 valence electron plus 1 charge. Alkaline earth metals, plus 2 charge. Maybe aluminum or gallium, plus 3 charge based upon them. The transition metals would likely lose their s electrons. The ones like tin and lead, which we've looked at previously, may lose some p and some d as well, but they could also lose some of their d or f, forming lots of different charges. And once again, knowing that it's possible to kind of explain, although we wouldn't have to predict each of those values. To say it one more time, if we're thinking about compounds, reactions, and predictions of what happens, the metals are predicted by their ionization energy. The more easily they lose electrons to form a specific ion, the more likely that's the compound they're going to make. Nonmetals, on the other side, tend to gain electrons. That gaining can be gaining to form an anion, or could be sharing to form covalent bonds in a compound. When they are gaining electrons, they tend to form a very predictable anion. Fluorine has 7 valence electrons. It likely gains 1 to form net, to have 8 to fill its sublevel. To gain 2 is very, very unlikely for that. Oxygen could gain just 1, but in gaining 2, it fills its energy levels. There is more repulsion, but with the way it interacts with other elements and atoms, or specifically ions, it often has the most stable end result when it forms -2. So forming these anions could require energy. It does increase repulsion, but we also increase attraction. And ultimately, with the compound that we end with, maybe ionic, maybe covalent, we end up with an end result that is much more stable. So with this, it's a really good transition to the next few units of attractions related to compounds. But it is important just to think about the valence themselves predict those things. They predict the ions, and they predict the ability to share and how they will share as well.